Okay, so this section is on section 2.8, related rates. So I want to go through two examples using related rates. This is a concept that employs the derivative and the chain rule extensively. So we'll talk about this and we'll work on some problems in class based on what we talk about here. So I want to start off with the first example, which is all it is I want you to just imagine a balloon in the shape of a sphere. So this is a spherical balloon. And it is being inflated with air. So we have air being pumped in. And we're going to stipulate that the air is being pumped in, so the volume is increasing at a rate of, let's say, 100 cubic centimeters per second. Okay. So we'd like to ask and answer the following question. So question, how fast is the radius growing? So the radius would be 1/2 the diameter. How fast is the radius growing when the diameter is 50 centimeters? Okay, so this is the question that we'd like to answer. And we have enough information, believe it or not, to answer this question. So, so let me give you the general strategy for answering a question like that. So the reason why these problems are called related rates is because we have one rate here, and that is the change in the volume, right? Volume increasing means the volume is changing. So that's a rate, and we're relating it to how fast the radius of this balloon. So the radius would be the distance from the center of the balloon to the edge of the balloon. And so if we have a balloon that's being filled with air, its volume is changing, but its radius is also changing. And so and these are called related rates problems because we will use calculus in order to relate these two rates to each other. So let me give you the basic breakdown of how to do a problem like this. So these are the steps to answer this question. So the first step is to identify the information that you have. So identify the info you have, and the info you want. Okay. So the info that we have is we have the rate of change of the volume. So, so the volume change, let's go ahead and just write this. So the volume, so this is the rate of change of the volume with respect to time. This quantity is equal to 100 cubic centimeters per second. So this is the first step, okay? And then the next thing that we have, so what we want is we want the radius change. At diameter 50 centimeters. Okay, so this we maybe will represent as another time derivative, the rate of change of the radius with respect to time. And again, this is at, let's say, well, if the diameter is 50, then the radius is 25. So we're looking for that rate of change when the radius is equal to 25. Great, so that's identifying what we need. The next step in our process is to relate the quantities V and R. Okay, so this is volume and this is radius. So let's relate these quantities. Well, we happen to know, or we probably know, a formula for the volume of a sphere based on its radius. It's okay if you don't remember this right off the top of your head. I'd give you a formula like this. But the volume, based on a particular radius, is 4/3 times pi times the cube of the radius. So this is the relationship here that we're looking for. Okay. And so now the next step involved is we are going to take the derivative of this equation with respect to t. So take the derivative with respect to t. Because in the end, we're looking for a derivative that's based on how time is changing. So that's so here's our equation. So we're going to take the derivative of it. All right. So what was the equation again? So this is still step 3. We're taking the derivative with respect to t of the volume function, and we know that this is equal to 4/3 pi r cubed. So we're taking the derivative of this with respect to t. Now, when we do this, well, on this side we're just taking the derivative with respect to t, so we get dv dt. It's taking the derivative of v on this side. Now here on this side we have a constant. 4/3 times pi is a constant, so when we take a derivative it just comes along for the ride. And then here we need to take the derivative of this function here with respect to t. But now remember, we're thinking of this as as something that depends on t. So r depends on t. So we use the chain rule when we take this derivative. So how does the chain rule work? So we've got an inside function. The inside function is r of t. So the inside is r of t. And the outside function is just cubing. So when we take this derivative using the chain rule, we get 4/3 pi times, so we have a power here, so we bring the power down, and then we drop the power by 1, leaving the inside function alone. And then we multiply by the derivative of the inside function. Now we don't know what the derivative of the inside function is, so we just signify it by writing it explicitly using calculus notation. So let's take this and clean it up a little bit. We've got dv dt is equal to 4 pi times the radius squared times dr dt. Okay, great. So that's the next step where we take the derivative of this. Okay, now we want to use this for the next step, and that is to plug in what we know. Okay, so what do we know? Well, we know that dv dt is equal to 100 because the volume was changing at 100 centimeters per second, and we know that r is equal to 25, okay, because the diameter was 50. Okay, so right at this, we use this location, consider right when the radius is equal to 25, and we know the volume is changing at this rate, so we plug those in and solve. Solve for dr dt. So let's plug those in. We get 100 is equal to 4 pi times 25 squared times dr dt. Okay, so this is all just a number. And if you solve this for dr dt, then what you get is you get 1 over 25 times pi. And of course, this is a length changing with time, so this is centimeters per second. And so the answer to this, dr dt, is, well, if we plug that number into our calculator, we'd get something that looks like this. 0.0127 centimeters per second, and this is the rate. The radius is changing. When the diameter is 50 centimeters. So this is our answer, and that was the original question. So if the balloon is being inflated and we know how the volume of the balloon is changing, then how do we compute how fast the radius of the balloon is changing? Okay, so that's example number 1. Let's do another example. Okay, so I'm going to draw a picture to depict what's going on here. So I want you to imagine that this is a wall, and this is the floor, and this is a ladder. And the ladder is 10 feet long. Okay. And suppose that, I'm on this ladder and I'm doing something and no one's holding the ladder, and unfortunately for me, the ladder starts to slide. So this is, the ladder is, a 10-foot ladder is now sliding, so I'm in great danger here. So I'm somewhere on this ladder, it's sliding, so the bottom of the ladder is moving away from the wall, and the top of the ladder is sticking to the wall but moving towards the floor. Okay, and so here's the question. If the bottom of the ladder is sliding at 1 foot per second, then how fast is the top sliding toward the floor? When the bottom is 6 feet from the wall? From the wall. I mean, of course, as this ladder slides, the rate at which this point right here is sliding towards the floor is going to change. So we really want to know right at the moment, right at the instant when this ladder is 6 feet away from the wall at the bottom, how fast is the top of the ladder sliding towards the floor? So that's our question, and this is a related rates question. And the reason it's a related rates question is because there's a rate at which this distance is changing, and there's a rate at which that distance is changing, and we're going to relate them using calculus. Okay, so let's go through the steps that we did in the last problem in the same way here. So the steps. So identify what you know and what you want. And I always put this in using a picture if necessary. It will almost always be necessary. That will be something you will probably learn as we go through more and more of these types of questions. So step 1 is identify what you know and what you want using a picture if necessary. So I'm just going to redraw this picture, and I'm going to put some unknowns, some letters here. So this is the letter sliding this way and sliding this way. This length is 10 right here, and then I'm going to call this length something. It's horizontal, so let's just call it x. And the same thing here, this is a vertical length, so let's call it y. Okay, so now here's what we know. So these are in feet, and we know that dx dt is equal to 1, okay, 1 foot per second, because this is the rate at which that number is changing, and it's growing. So it's growing at 1 foot per second in that direction, so this is the rate. What we want is we want this when x is equal to 6. Okay, so this is what we know, what we have, and this is what we want. Okay, so we've taken our unknowns and our knowns and written them out in math using some related rates. Okay, so now step 2 in this process was relate the quantities. Okay, so here's how I see them related. This is a right triangle right here. So we know x and y are related to 10 by the Pythagorean theorem. So x squared plus y squared is equal to 100. So this is the Pythagorean theorem based on the triangle. So this is Pythagoras right there. Okay, that was step 2. Now, our next step was to take the derivative of that. So step 3, take d dt. Okay, so we have the derivative with respect to t of x squared plus y squared is equal to the derivative with respect to t of 100. Okay, so now, well, one side of this is easy. The derivative of a constant is always equal to 0. And the derivative here, well, this is the derivative of the pieces. So we're taking the derivative of x squared plus the derivative of y squared. Okay, so now for both of these, we need to use the chain rule. All right, so because in both of these cases, x and y both depend on t. So these both depend on t. Because they're quantities that are changing with time. Remember, this was the picture. Here was x, here was y. X is changing with time, and so is y. Okay, so they both depend on t, and so we have to use the chain rule. So we do that. The outside function is squared, so we bring the 2 down and leave the inside function alone, and then we multiply by the derivative of the inside. Okay, same thing here. We bring the 2 down, leave the inside function alone, drop the power by 1, that's what we did here as well, and then multiply by the derivative of the inside function. So again, this was the chain rule that we used in this step. Okay, good. There's a 2 here and a 2 here and a 0, so let's just divide those away. Okay, and then step 4, plug in what you know and solve. Okay, so what do we know? We know x is equal to 6. We know that dx dt is equal to 1. Y is a little bit trickier, but not too tricky. Remember, y we can get from taking the equation x squared plus y squared equals 100. So if x is equal to 6, we get 36 plus y squared is equal to 100, which means that y is equal to 8. Okay, so we know these, this, and we plug these into our equation right here, and we get 6 times 1 plus 8 times dy dt is equal to 0. Okay, and if you solve for this, you'll get dy dt is equal to minus 3/4. And of course, the units here are feet per second. Okay, so that means that right at the moment that the ladder is 6 feet away from the wall, the top of the ladder is sliding down at 3/4 of a foot per second. Okay, so that's the answer to this question right here. Okay, this is a short section. The best way to learn how to do these is by example. So here's your homework. I want you to read on page 179 of the textbook, problem-solving strategies. Okay, and example 4. Okay, have this done by Thursday. Great.